have additional manufacturing facilities and sales offices throughout the US and Europe. And very similar to our pulse generators, that can be said about our RF division as well. We've had some huge growth over the years. Now we are recognized as one of the leaders with not only high frequencies, but very high performing solutions. So I mentioned our vast network of sales offices. Here's a quick example. We have a network of sales representatives across the US. Just a quick snapshot here of where they are located. So wherever you are located, we most likely will have a local representative that can support you there. Please feel free to reach out, and we are happy to direct you to the right person. This is just our contact information, and again, as David mentioned, we will provide the slides and the recording of this webinar to all of our participants. So if you're really interested to find out exactly where your local rep is located, you can easily look back to this slide and get their contact information. And worldwide as well, not just here in the US, but we have a network of representatives all over the world, from Asia, Europe, North America, South America. We do appreciate the support from all of our reps all around the world. And again, if you have questions on your local rep, please do let us know. We're happy to direct you to the right person. So the agenda for today. First, I will be going over phase noise. What is phase noise? How is it measured? The types of measurements, including the types of references. And then John Lauder will give us a real-time demo of our ATE, or Advanced Testing Environment solution. Give you a real-time demo along with a real-time demo of the GUI that we will provide with the benchtop application. So he will go over the different features and functions and give you a real-time demo of some measurements as well. And then I will dive into our signal sources, touching on the basics of an antenna measurement system. We will explore the different models that we have to offer. And then Mr. Manuel Haegler will give us a live demonstration of phase coherency using our multi-channel solutions. He'll also touch on our exclusive option of phase coherent switching. And then at the end, we'll take a quick sneak peek of our new product coming down the line, our vector signal generator. And finally, we'll have our Q&A session. So let us dive right in. The main question here, what is phase noise? Now, the definition or vocabulary definition is phase noise is the frequency stability of a signal, more specifically within an oscillator. Now, if you can imagine a cell phone connection, you're speaking with someone on the other line, and if there is noise in the background or the voice is getting choppy, not clear at all, well, phase noise has a lot to do with that communication. That includes radar, satellite links as well. So as you can see, phase noise is very important, especially for manufacturers that are producing low noise devices. You may have heard of phase jitter, or just jitter in itself. That's essentially the same thing as phase noise, except that jitter is represented in the time domain, while phase noise is represented in the frequency domain. So if you look at the images on the right here, the first says an ideal signal. That's quote unquote what the ideal signal is, what everybody is really striving for. And as you can see, nominal amplitude, nominal frequency, a very clean sine wave, and the spectral density line below is very straight and narrow and very clean as well. Now, again, that's the quote unquote ideal signal, which is not what we will see in the real world. So that image you see on the right, that is what you would expect. Fluctuations, amplitude changes, phase changes. You see the sine wave there is not as clean anymore. The spectral density line below is not as straight anymore either. Very, very buzzy. So again, phase noise is very important, and many manufacturers would need to know what their devices are producing there. So brings us to the question, how do we measure phase noise? Now, there are basically three ways to measure phase noise. The first, many of you already know, is the spectrum analyzer. That's the oldest and simplest method. You basically get your device under test, hook it up to your spec an, and go and start doing your measurements. Now, there are some limitations. The main limitation is the noise floor of the spec an itself. That must be lower than your DUT. Your dynamic range as well is very limited because the signal is not suppressed, and there's no way to distinguish AM from PM noise, which is also highly important. The second method is the phase detector technique. So basically, your device under test, that signal is mixed with a reference signal at the same frequency using a phase detector mixer. Now, there are some limitations to this as well. That reference source, very similar to the spec an, must have a lower noise floor than your DUT in itself. The PLL also forms a high pass filter as it's trying to compensate for these phase fluctuations. That PLL loop bandwidth must also be much lower than the lowest required noise frequency. Now, this is partly what we offer as a solution with our PNT. And I will dive into how we try to tackle some of these limitations in the next couple of slides, but must also touch on the third way to measure phase noise. That is IQ demodulation. So basically, you are down converting your signal into baseband and measure it directly with an analog to digital converter. The main limitation to this here, if you would even call it a limitation, is your dynamic range. Basically, that your phase noise tester must have multiple ADCs built in to measure simultaneously. Now, again, this is all going to depend on your budget, if it's a limitation or not. Out of my research and the manufacturers that, the types of methods that they offer, I've only found one that does IQ demodulation. It is not Keysight, it is not us. So I will let you take the wild guess. So we talked about the phase detector technique and some of those limitations. This is the answer to try to mitigate some of those limitations, which is the cross-correlation method. Now, this solves a problem of the reference source noise by using two independent reference sources and phase detector circuits. So now, instead of just having one, now you have two. Those will be mixed with your signal, and the outputs can now be averaged. You can average the noise from those reference sources away by cross correlation. Therefore, you can have an improvement by about 20 dB over the single channel quadrature method. Here's a quick visual of cross correlation in itself. So as you can see, the signal source under test, your DUT will pump out a signal. It will get split into two channels. And again, each channel has a built-in internal reference. And that reference signal will be mixed with your DUT signal. The outputs will come out to the digital signal processing unit. And this is where the cross correlation happens. You will average away that extra noise. And you can expect some improvements in your measurements. If you look below here, the number of correlations that will determine how much improvement that you will get. So for example, 10 correlations, you can expect about a -5 dB improvement. 10,000 correlations, you can expect about a -20 dB improvement. So let us dive into the types of measurements. Absolute measurement, the most common, the most requested. This is basically the phase noise measured on the output signal of a one-port device. So for example, your device under test could be any one of these oscillators or a signal generator, VCOs, OCXOs, TCXOs, basically the signal source. If that's what you are measuring, then that is an absolute measurement. But we also know that not everyone is measuring the signal source. Therefore, additive and residual measurements are necessary. So additive phase noise, also known as residual, is the self-phase noise of a component that adds to an existing signal as the signal passes through it. So for example, amplifier, transmitters, mixers, and any non-self-oscillating device. These devices have the signal from the signal source passing through it. While it does that, these devices are also going to add noise to that signal. So as a manufacturer, you would need to know how much noise is actually adding to that signal. So hence the additive measurements and something that we proudly provide with our PNT. This is a quick snapshot of one of the ways you can set up for an additive measurement. In this case, you are using both channels. DUT, let's say, for example, is an amplifier. You have your oscillator there as the external reference and your phase shifters to make sure that you are within quadrature before you perform the measurement. Another way to set up here, this is just using one channel. Again, DUT could be an amplifier that is being split with a signal generator and your phase shifter to make sure you're within quadrature. And again, John Lauder will dive into a little bit more deeply with this real-time demo. A quick snapshot of the GUI, what you would see for the additive. Sorry that you don't see much activity there and there's not really much to show. This is just a general image, but again, John Lauder will do a real-time measurement of an additive measurement, and you will see exactly what the results will look like. So let us dive into the references. We spoke of the internal references before and how our PNT has two built in, and that is quite advantageous. But there is some limitations there as well. If you are still looking for some better noise floors, aside from using internal references, then maybe external references could be of a solution for you. So before I get into that, let me explain what is an internal reference. Well, that is basically a synthesizer or a signal source. But it must have some components to make that frequency flexible. So for example, our PNT that goes up to 40 gigs, your references that are built in must also go up to 40 gigs. And those components that let you get up to those frequencies, those components are going to add some noise. So by using external references that do not have those components, you can expect some better noise measurements. So for example, let's say in the OCXO at a certain frequency, 3 gig frequency, and your DUT is also a 3 gig OCXO. Therefore, you don't have any components anymore. It's just the signal itself. Therefore, you should be able to get much better measurements than using internal references. A quick snapshot of some our models of the phase noise tester. Now, our first iteration is the model 7070 going up to 7 gigs. We have the 7300 going up to 26 gigs, and the 7340 going up to 40 gigs. Again, both be able to provide absolute and additive measurements, also amplitude measurements. This is all in one package, as there's no additional cost. And then a host of other features as well that John Lauder will get into, but I must highlight the one-step VCO characterization. This is a very popular feature many of our oscillator manufacturers are implementing now. Some key features again, as you can see from the picture, there is no front panel with an LCD screen and buttons and knobs. Things or those devices or those components tend to go bad over time. So we have completely removed it. Everything is completely PC controlled with the GUI software that we provide for you. You can even control it remotely through LAN, USB, or even GPIB. And I must also mention that not having the extra, LCD screen and the buttons in the front, that allows us to reduce the cost significantly for this unit, but still not sacrificing any type of performance. Must mention the low instrument noise floor spec. This is, I would say, one of the most important specs. Again, the device that you are measuring your DUT with, that device must have a lower noise floor than your DUT. That is the main theme. Minus 190s is a very, very low noise floor, so it should be able to cover many of our customers' needs. Offset range, again, is very vast as well, from 0.01 hertz to 100 megahertz. Must also mention the supply, DC supply voltages, that are built in to the unit. Again, very beneficial, especially for your VCO characterization. You can even trigger this unit externally with another device. Very lightweight, about 24 pounds. 24 pounds, so you will not need a dolly or a cart or anything to move from one location to the next. Now, these are, again, some more key functions, but I wanted to highlight the amplitude noise measurement. Again, this is something that we offer at no additional cost. This is standard. All the basic measurements, whether it's absolute, additive, or amplitude, these are all standard with our unit. Okay, let's put the lunch in Lunch and Learn. I know many of you are thinking, how are you even calling this a Lunch and Learn? Where is the lunch? Well, we thought of this as well. And in our appreciation for you taking the time to join us today, we will send you a gift card to a local restaurant in your area. I mean, I do not know what restaurant it is at the moment, but I can promise you that it is not going to be Wendy's. Now, with that said, I'm going to pop up this button on your screen. You should see it in just 1 second. Boom. Now, if you click on that button, it'll take you to our contact form page. Please go ahead and fill in your information, where you would like to send us your gift card. And please also fill in what size t-shirt that you wear, as we will send you one of our Berkeley Nucleonics t-shirts as well. Okay, moving on. Quick touch on ATE before John gives us his real-time demo. Yes, this is another feature that we are proud to offer in addition to our benchtop application. Controlling the unit with Skippy commands, whether through USB, GPIB, or Ethernet, and a host of programming languages that we support, whether it's Java, MATLAB, or LabVIEW. Most recently, we've added Python, which is what John will show you with his ATE demo. Now, with that said, John, the floor is yours, sir.
Thank you, Junior, and good morning, everyone, or good evening to the rest of the world. As Junior mentioned earlier, we will be doing a quick tour and a demo of the Signal Source Analyzer, GOI, and a short demo of the ATE. The ATE is built with simplicity and ease of use in mind. The functions are split into tabs for easy access. The first tab is absolute phase noise. This is probably the most used function of the Signal Source Analyzer. Let's connect to the device. Connection to the device is very straightforward. Simply click the device, click Connect, and select the device you want to connect to. So I'll be connecting to the device. Once connected, the GOI automatically detects the frequency and the power of your signal. All you have to do from this point is set your offset frequencies maybe the number of correlations. I'll set it to 5, for example, and click measure. Once measurement is completed, you can proceed with the analysis or do a post-processing like setting up the markers, checking spurs, or simply saving the file and sharing it with your colleagues. Also on this tab, you can activate and measure pulse mostly for radar systems. The second tab is the additive phase noise, or commonly known as the residual phase noise. Again, as like Junior said, this is for non-oscillating device like a low noise amplifier or passive devices like attenuators and cables. With additive phase noise, you will need to decide whether you use a one correlation, one channel, or two channel cross correlations. A two channel cross correlation will yield a lower phase noise floor. Let me set that one up. Once you complete your connection using either one channel or maybe a two channel, you will need to calibrate your setup to set both reference signals and in quadrature with the DUT signals using the two phase shifters. Here we start calibrate our signals. As you can see that my references are already in quadrature with my DUT signal. It also shows it on the GUI that as the measure button turns green. From this point, you can just click measure again. This is the noise floor of this is the phase noise floor of my device. To quickly show you how it looks like if your reference are not in phase or not in quadrature with your DUT. Let me shift the phase noise. And it says adjust the phase. Next tab. Next tab is the amplitude noise. This is very similar to the absolute phase noise, except that this measures the variation of the amplitude. Next is the high drift absolute phase noise tab. This again looks very similar to the absolute phase noise, except it's more focused on a drifty source or oscillator, like the YIG, DRO, and SAW, to name few. The fast Fourier transform or FFT analyzer. This is a baseband noise analyzer to measure from 1 Hz to 100 megahertz frequency input. This input uses the rear panel of the device, the baseband. Next is the transient analyzer tab. This is mainly used to measure and analyze the transient behavior of signal. Also on this tab is a burst analysis function, of which it allows you to measure a very narrow pulse RF. The time stability tab. This is for long-term measurement of an oscillator or device, like measuring the long-term drift or aging of an oscillator. As Junior mentioned earlier, we have the VCO characterization. This is a very powerful tab or tool in characterizing and optimizing the performance of your VCO. Here we have the frequency versus tune voltage, the sensitivity of your VCO, the supply current, and the output power of your VCO. We also measure the pushing of your VCO and a phase noise at the same time. Again, you can enable or disable each test depending on your applications. Lastly is the spectrum monitoring tab. As most RF workbench, almost always in need of a spectrum analyzer to monitor or verify the frequency and power, but not necessarily to analyze in details the signal. We added this feature to eliminate, or so you don't need an expensive spectrum analyzer in addition to SSA. This, by the way, measures up to 42 gigahertz. Now let's go for a quick demo of the ATA mode. ATE basically consists of a hardware and a software. A hardware, for example, is an SSA, like our PNT, a signal generator, or maybe a spectrum analyzer. And a software may be a custom software written in LabVIEW, C++, Java, and Python, or maybe some other programming languages. What we have here is a Python script to measure the frequency, power, and a phase noise of a given signal. Like what we did in GUI, the very first thing to do is to initiate a connection to the device. That's what we do here. You can either, again, use USB or LAN. After connection, the very first thing to do is to reset the unit to a factory default using the command reset *reset. This is to make sure to avoid conflicts of the current setting of to your new settings. Next is to activate the automatic frequency search and automatic power search. This can be optional too if you already know the power and frequency of your signal. Next group is setting the parameters of your SSA or PNT. What I have here is the default settings, of which you can omit this if you don't need to customize your SSA. So again, this is the default parameters. This group over here. And then the next group is setting the averages, number of correlations, and offsets of your device. This is similar to what we did on the GUI earlier. And then we set a loop to make sure the device will finish reading all the phase noise data before proceeding to the next stage or commands. Next command is we query the frequency and phase data of what we read earlier, and we save it to a variable. This is what the engineer can crunch or display as a graph. Here I use the Python 5 plot to display the data. Now let me run the data or the script using command F5. That's the output of the phase plot as measured by the ATGOI, and the data. Let me just move that one over here. This is the phase data or frequency data, what we read over here, frequency, and the second one is the another block of data for the phase noise. So again, this is, if you look at the plots, this is the X and Y of the trace. So if you just want to see the block data, again, those are huge numbers. Those are the frequency, and this is the phase. That concludes our live demo, and let me give you back to Junior to talk more about signal sources.
Thank you, John. Thank you, John. Now, since we've went over our PNT and the different functions, let me dive into our signal sources. Before I do, I will touch on the different types of signal source solutions that are on the market. Now, the first is the continuous wave, CW, the most requested. Some may even call it a LO source. The second is an analog signal generator, usually with some modulation capabilities. And then finally, there is the vector signal generators, VSGs. They're capable of both the analog and digital modulation. Now, the quote-unquote golden source in a lab setting, this is usually a high-performance CW or LO source. Usually high performance meaning very, very, very low phase noise. And sometimes an analog signal generator if you need some modulation capabilities. The most functional out of them all is the vector signal generator, again, being able to provide digital, analog, and even sometimes pulse modulation. Now, let me touch on antenna measurements and the basics of an antenna measurement system. Now, the key components here, the first is the shielded chamber with positioning system. Then we have the position controller, which is basically the interface to this positioning system. Your signal source, obviously, for example, one of our BNC units with fast switching. I've highlighted fast as I will get into why that is important in antenna measurements in the next couple of slides. And then the receiving side, it usually consists of a VNA, spectrum analyzer, frequency converter, usually a combination of all three. And then finally, the software. Many consider this the heart of the antenna measurement system, as no matter how good your hardware may be, if you don't have the software to drive it, then your results may not be what you expect. So this is just a visual of a basic antenna measurement system. There are some different applications, near field, usually indoor, shorter distance antenna testing, far field, obviously usually outdoors, longer distances, and then RCS or radar cross section measurements. That is to test objects or vehicles, see how well they can be detected by radar. Now, if you look at the image, we have our signal source as the transmitting side, right? So that signal will go to the antenna. Also, the signal will be split as a reference channel going to the receiver just to make sure your frequencies are matching and stable. And then on the receiving side, you even have a probe antenna, also to measure any type of electromagnetic fields or interference. So we mentioned the shielded chamber with positioning system as the first key component. This is a quick snapshot of what one chamber would look like. As you can see, the walls, the ceilings, the floors are all covered with this electromagnetic absorbing material. That is basically to suppress any type of reflections or interference to ensure that your antenna under test that signal is not interfered with. Now, if you look to the right, that is the actual positioner. So if you can imagine the antenna mounted on top, that positioner will rotate the antenna 360 degrees at the intervals or increments of your choice. Now, I mentioned fast switching earlier, and why that would be important. Well, in this case, if you can imagine the antenna, while it, travels in that 360 degree space, you are able to measure many more frequencies, do much more measurements in the same amount of time. So if your signal source has fast switching speed or fast frequency sweeping speeds, that's going to allow you to do more measurements, but also allow you to be much more productive as well. So very important for antenna manufacturers or any measurement companies. They all request, what is your switching speed of your signal sources. So speaking of our solutions and how they can fit in, let me highlight our first iteration here. It is the low noise microwave synthesizer. We have a few different models, model 845 or the 865-M, going up to 40 gigs. Excellent phase noise. This is one of the most important specs that we care about, minus 118 at 10 gigs. Power is very great as well, plus 23 typical throughout the frequency band, and fast switching speeds, again, 25 microseconds. Let me quickly switch to my camera here so I can show you exactly what one looks like. So hopefully you can see me.
Looks good, Junior.
So this is the 865-M synthesizer going up to 40 gigs. As you can see, it's very small, compact. It's lightweight. I would say about 3 pounds. Easily, move from one location to the next, not a problem, but also integratable, into your own system. If you're developing a system that requires maybe a reference source within, we can even support you on helping you integrate this into your chassis. But, the front panel here, you have your SMA connector output for your RF out. Then you have some BNC connectors for other functions like your reference in and out. We even have pulse capability with this synthesizer, and a trigger for if you wanted to get this started with a different device. And then a host of connections. You have your USB and LAN and your power supply connection. But again, very compact, very light, but the performance is there, especially with that phase noise. So let me click back. Moving on. If you needed even a smaller form factor, we actually have an OEM solution. So the picture here shows you the board level module of our benchtop signal generator. So you may require a little bit more functionality as well with some modulation capabilities. This could be a better solution than our synthesizer. So the specs are all still there for you. Very high power, excellent phase noise, minus 100 at 10 gigs, 30 microsecond switching speed, and all of our signal generators can be phase locked. So if you have multiple, OEM units or multiple benchtops, you can easily phase lock them together. So moving on, I just showed you the guts of our benchtop signal generator. Let us talk about the benchtop in itself now. So as you see from the picture here, not the traditional form factor, traditional enclosure that you would expect. It's very small, lightweight, easily moving from one location to the next. It's completely portable. Again, frequency ranges going up to 40 gigs. In this case, even faster switching speeds, 20 micro with the option of the fast switching option. Modulation capabilities are all there as well, AM, FM, PM, as you would expect, but we also have pulse modulation. Excellent phase noise. We're always going to harp on that. In this case, it's minus 113 at 10 gigs. So let me switch back to my camera so I can show you what the benchtop looks like. So, again, as I mentioned, very small, compact, portable. You have a handle on the side. It's about, I'd say about 6 pounds. So you do not need a dolly or a cart to move it anywhere. Colleagues can easily come and take it to their lab if they need. Also built for field use. Take it out to the field. Very popular for that as well. This is one of the options we have for field use to make it a little bit more rugged. It's a little bumper for the front and the back. Hopefully I can handle this without dropping it. There you go. Yeah, about the size of a lunchbox, right? So if you look at the front panel, you know, you have the choice to set all your parameters through the front panel. You have your LCD screen, your knob and buttons to set the frequencies and power. Now, you know, the GUI that we provide for the synthesizer is also available for this. It's completely free. So you have the choice to, you know, manually set your settings or through a PC remotely, right? You have your SMA connector for the RF out again, you know, and your controls. In the back, you have your rest of your BNC connectors, whether it's a reference in and out, your pulse, you know, and the trigger as well, and so forth. Have some connections for your communication, your LAN, your USB. And if you are using GPIB and that's what you require, we do have that option as well. But yeah, very easy to use without sacrificing any type of performance. Okay, so let me switch it back here. That was our benchtop single channel unit. But we must also touch on our multi-channel. We're very excited about this as well. As you can see from the images, we have a couple different form factors. You know, the frequency range going up to 40 gigs. One sec here, let me switch this back. There we go. Going up to 40 gigs, 2, 3, or 4 channels. 4 channels maximum for the 1U slim enclosure that you see there, the first image. If you needed more than 4 channels, then you can see the image below. That is basically the same enclosure as our PNT, but this is basically an 8-channel signal generator. So whatever your needs are there, please let us know and we can support you. Now, specs are all there. You know, same as our single channel. We have very fast frequency switching times to 25 micro. And I would say most importantly, because this is the main question all of our customers ask for people who are interested in our multi-channels is, hey, are your outputs phase coherent? Yes, that is standard for all of our multi-channels. And with that said, I'd like to introduce Manuel Haegler. You know, he is the expert on our multi-channels. He will go over, you know, phase coherency, the terminology, and then also our exclusive option of phase coherent switching and how that can be a benefit for you. So with that said, let me pass it over to Manuel. The floor is yours, sir.
Thank you, Junior. So today I would like to talk about phase coherence in multi-channel systems. So I will talk about phase coherence between several signals, phase coherent switching, phase memory, and phase matched outputs. So first, let's define what phase coherent signals are. We say that 2 signals are phase coherent if the phase relationship between them remains constant over time. So if you look at these signals at a certain time and measure the relative phase, we are sure that at any time in the future, the relative phase remains the same. One application for which phase coherent signals are very important is quantum computing. A quantum computer, instead of having bits, as we know from our computers and cell phones, they are so-called qubits. In order to create a system that is stable and can make calculations, those qubits must be entangled, or in other words, linked to each other. This means that influencing one qubit will influence all the others. So how can we achieve this entanglement? We need to be able to control each of those qubits with a signal that is phase coherent with the signals controlling all other qubits. If we can do that, the qubits are coherent and we have a system. So now all our multi-channel systems have phase coherent outputs, as Junior mentioned. There's also the possibility to add phase coherent switching, which is also known as the PHS option. So let's see what phase coherent switching actually is. We say that two signals are phase coherently switched when the relative phase is deterministic and always has the same value when we set the signals to the same frequency. I prepared a short video that demonstrates this behavior and gives a little bit more insight into it. Let me start it for you. In this short animation, we will look at two channels of a signal. Explanation about what exactly happens. So during this first part, both channels run at the same frequency f1. The relative phase is 0 degrees, the biggest match. Then at this moment, we switch both signals to different frequencies. Now we have channel A running at frequency f2 and channel B running at frequency f3. At this stage, the channels are phase coherently switched, but it is a little hard to see since we set them to some random frequencies f2 and f3. Here we switch channel A back to frequency f1, and then here we switch channel B back to frequency f1 as well. We can see that when this happens, the relative phase between the channels is back to 0 degrees. In more general terms, when two channels are phase coherently switched, their phase relation is deterministic for all frequencies. In this example, when both channels are set to f1, the relative phase is always 0 degrees. If they are both set to frequency f2, their relative phase would be 30 degrees, for instance. This would be true each time they run at frequency f2. All right. So now, for what kind of application can phase coherent switching be used? In phased arrays, for example, it's possible to change the direction of the waves by setting a phase shift between different antennas. Having outputs that are phase coherently switched can greatly simplify the work, since the phase relation between two signals is known when switching them to a certain frequency. Then another concept that we implement in our multi-channel systems is phase memory. So what is phase memory? That means when we have a signal that runs at a certain frequency f1, then it's switched to another frequency and back to the initial frequency f1, behaves as if it had been running at the initial frequency f1 for the whole time. To illustrate this, I have another short video with some comments. Short video, we will look at a single channel unit showing the phase behavior of its output being switched between two frequencies. Let's first go through the animation, after which we will have a more detailed look at what we see. So here in the beginning, the signal is running at frequency f1. We then change the frequency to frequency f2, show with the blue dotted trace how the signal would look like if it had remained at frequency f1. Here it is hard to tell if there is a particular relationship between the two traces. We then switch the signal back to frequency f1, and we can see that the signal matches the imaginary dotted trace. Signal behaves as if it had been running at frequency f1 the whole time. In other words, if we measure the phase of the signal at the time t0, we know exactly what phase the signal will have at time t1 if at both times t0 and t1 signal is set to the same frequency. The time in between t0 and t1 we can change the frequency of the signal as much as we like. All right. So finally, another feature that we have in our multi-channel units is phased match outputs. This means that the output signals of all channels have a relative phase of 0 degrees at all output frequencies. Phase matched outputs requires having phase coherent switching. With a phase coherent switching capability, we know that when setting two channels to 1 GHz, for example, they will have a relative phase of, let's say, 40 degrees, always. When we set them to 2 GHz, they will have a relative phase of maybe 75 degrees. We know that this is always the case. When we have phase-matched outputs, though, we have the additional information that at the same frequency, the relative phase between the channels is always 0, no matter the frequency that we program. This makes programming phased arrays even easier. I have one final video to illustrate this for you. In this short animated video, we take a look at a multi-channel generator with matched outputs. We'll give a detailed explanation of what is being shown after we played through. So here in the beginning, we have both channels running at the same frequency f1. As we can see, the relative phase between the two signals is 0 degrees. The peaks of both signals match. Then we switch the frequency of channel A to frequency f2, and shortly after we follow by switching the frequency of channel B to the same frequency f2. Again, we see that the relative phase between the two signals is 0 degrees. One more time, we switch the frequency of channel A to f3, and we follow by switching the frequency of channel B to f3 as well. One more time, we see that the phase between the two signals is 0 degrees. This is true whenever we set the channels to the same frequency. They will always have a relative phase of 0 degrees. We can see that the phase coherent switching is a necessary condition to achieve phase matched outputs. Now, of course, if we attach cables with different physical characteristics to the outputs of those two channels, their phases would not match. The firmware of our Model 855 supports a command that allows to compensate for mismatching cable length and therefore achieve phase matching independently of the cabling used at the output of the channels. All right. So as we've seen when talking about phase coherency, there are many characteristics that need to be defined. Our multi-channel systems are always phase coherent, and when adding the option PHS, they are enhanced with phase coherent switching, phase memory, and phase match outputs, all of which can greatly simplify the implementation of challenging and demanding applications. Thank you very much for your attention, and back to you, Junior.
Thank you, Manuel. So we are approaching the finish line. And as I mentioned before, we want to touch on our new products coming down the line. And we're very excited about this one here, the Model 875 Vector Signal Generator. You know, over the years, all of our, benchtop signal generator or synthesizer customers were requesting, I would like to see some IQ modulation. When are you guys going to start providing something like that? So we've taken that to heed and went to the drawing board, and now we're very excited to announce our Model 875. Frequency range will again go up to 40 gigs, but we will have a few different models coming out at different times. So the first two iterations will be the 4 and 6 gig models, which will be available at the end of this month in July. And then we'll have the 20 and 40 gig models that will be available at the end of this year. So please keep your eyes posted to us if you need the higher frequencies. Now we are offering the IQ modulation along with all the other modulation that you require, from a regular signal generator, AM, PM, FM, and of course offering pulse and chirp as well. Ultra high IQ data rates, deep internal memory, meaning you have plenty of space to save as many waveforms as you like. Again, we're always going to harp on this excellent phase noise for many different applications. And this may be even exclusive to us here, the wideband linear chirp function. That is for customers who are using the spread spectrum technique for their applications. Again, if you have any IQ modulation requirements, please do feel free to reach out to us. We are happy to validate and support you. So, almost there. I must mention our BNC Academy. You know, we're very excited about this as well. We've recently launched our online courses. The courses range from different topics, you know, a variety of different topics, from RF fundamentals, phase noise measurements. We even have a test and measurement and precision timing course, and then courses for our nuclear side as well. I will actually pop up another button for you. In this case, this is a free code to access any of our courses, even if maybe you're just interested in nuclear and want to try it out. You're more than you're more than welcome to. The code itself is Berkeley in all caps, and once you click on that, it'll take you. It'll take you to this page. You know, our Academy page. You see on the left here, those are our list of courses, and once you choose which course you would like to take, you click on that and it'll take you to a credit card form. Yes, there is a charge for these courses, but again, in that credit card form, there is a slot where you can type in this Berkeley code. Then it'll reduce that number to 0 and off you go. Only thing we ask in return is that if you do take the course, let us know your thoughts. We need feedback. We appreciate your feedback. We are continually trying to perfect these courses, and you know, we cannot do this without your thoughts. So please do let us know. So that brings us to the conclusion. Thank you again for taking the time to be with us. Let us begin our Q&A session. I know there's a few questions in there already. I think David's been tackling them on the way. So I don't know, David, you want to pick out some questions that we can maybe? I think you're muted right now, though. Uh-oh.
How about now?
Yeah, we can hear you now.
Okay, yeah, I think so we can certainly drop questions in the Q&A. There's just too many people to do the open forum. Looks like about just 90 people or something. So we'll just do the Q&A for now. If you want to drop questions in here, we'd love to hear from you. If you have more sensitive questions about your application, you can email the information that's right there on the screen, and we can get right back to you as well. We're around for the next hour or two to tackle some of these more important issues. Got a question from Alexander on primary markets. Alexander, the markets are so widespread for RF test equipment. Hard to narrow that down. It's an exciting field we're in. Things changing all the time with IoT and 5G and communication, just the breadth of communication applications around the world. So one of the reasons I love to be involved in this is because of the variety of applications. So thank you for the question, but there's not a quick, easy answer for that. Another question there about can you add attenuator? Adding attenuator. I don't know if John wants to tackle that one. The attenuator in between the two phase shifters to increase your isolation.
That's actually my answer to Kevin Zhang on his question earlier.
Mm-hmm.
So when using a noisy, what is the question? Noisy, less good sources will make sources less noisy. That's my question. And he also asked about the injection. So yeah, so to increase isolation, you will need to use some attenuator in between your phase shifters, and the DUT. My setup, I have about 3 dB attenuator.
Okay. Thank you, John. Great. Anything else for Manuel or John on the phase coherency or the ATE mode, the high-speed ATE mode for the phase noise tester? Again, thank you for the wide range of people who've joined us on the webinar today. I know for many of you, it's sort of late in the day. We tried to pick a time that would be most convenient for everybody. Robert asks about an internal LO source that can be used for a phased array antenna.
Yes. Let me just jump in here real quick. Yes, we do. Matter of fact, we are working on an application like this with one of our customers, and our low noise synthesizer, the 865M that I just showed off, that is being used as the internal LO source for their system. So yeah, let us know, and we're happy to work with you directly.